All right. So for electric energy, in addition to electrical force, which is what we did last day, and remind you that the equation looks almost identical to gravity, except that it's a force between charges instead of forces between mass. Now, just like gravity, electrical force are also associated with a field, a force field. Gravity, the field is called gravitational field. For electricity, we have electric field. So very similar to gravity, the field depends on two things. Depends on distance from the planet, and also, well, not from the planet, distance from the charge, and also it depends on the size of the charge, right? Distance from and the size of the charge. So in fact, we define electric field as the amount of force that you will get per unit charge. So electric field is defined as the amount of electric force that you will get per unit charge. So it's force divided by charge. It's force divided by charge. Now, if you look at the unit, how do you figure out the unit? Pretty easy. Force is measured in Newton. Charge is measured in Coulomb. So not surprisingly, and not very original either, the unit for charge is Newton per Coulomb. For field is Newton per Coulomb. So electric field has a unit of Newton per Coulomb. Right? So if you look at the equation, so Newton on top, Coulomb on the bottom. Unfortunately, right, electric field use the symbol E, which I know is very easily confused with energy, but this E is a vector. It does have a direction, where energy doesn't have direction. So that's the only difference I can tell. So E stands for electric field. Well, electric field. So E field, electric field, right? And force, right? Force is the electric force is Fe. So electric force, and Q is the charge. Now, and then we put the equation, electrical force equation together. So electrical force from last day is Coulomb constant, Q1, Q2 over R squared. So if you take this equation and you say, oh yeah, let's divide this by charge, then what happened? Well, then one of the charge is gone. So if you take this and then you say, okay, yeah, just divide it by charge, then you're going to get a electric field equation. So basically, that means one of the charge is gone. Right? So you take that equation, you divide by charge, so you get one less charge on it. So now it's just 1Q. Okay, now still, no direction can be tell from the equation itself. So we are still using this for magnitude only. For anything to do with direction, you have to draw a picture. So magnitude only. So for direction, use diagram. So exactly the same thing as the force equation last day. Okay. But the equation itself shouldn't be too hard to deal with because it's just Coulomb constant multiplied by charge dividing by the distance from that charge square. So since we're dealing with an examples of another force field, so force field, therefore, we have to remember that the field is a vector quantity. That means it does have a direction. So if you only have one, you're only looking for the field from one object, then it can point in any direction away from the charge or toward the charge. So let me show you some diagram. Okay. So when you draw a electric field diagram, so you always draw the field line as, okay, so that's actually not enough space over there, so I'll write it down here. So the field line, the electrical field line is the direction, okay, so it's the direction that a positive, okay, a positive test charge, so a positive test charge would, so the direction of the electric field is the direction that a positive test charge would move in the field. Okay, so I'll explain what that means by just drawing a picture. okay, by drawing a diagram. Okay, so now here, down here, we have a space. So we're going to draw a proton and a electron. So here we go, proton. Proton is positive. So the electric field diagram from a proton looks something like this. So it's just a whole bunch of arrow that points outward. So we will say proton has this kind of electric field. Okay, it's just, so these, every single one of these lines are electric field. Okay, so now this is a 2D picture of it. In reality, it's 3D. So it's more like you can look at it in every single direction in space, and you have these like invisible force field line going through the space. And the further you are away from the center, the weaker the field is, and so on. Now, but what does these line actually represent is what happened if you somehow bring in a, let's say a little tiny positive charge get lost in space, and then we pick it up. We say like, okay, hey, we call this thing a test charge. That means a little charge, from space that we just use to test out things. So we take up this test charge, and we then move it, for example, to this location. And then we ask, what happened if you have an extra charge at this location? Well, then this charge is going to repel and go up, right? Or what happened if I put that little charge down here? It will go down. What if I put that little charge on so let's say on the left or on the right? So what if I put that little test charge, for example, over, so let's say if I can move it over here. So what if I put that little test charge, let's say at this location? Wait 1 second. Let me see if, yeah, okay, there we go. Okay, okay. So what if I put that little test charge in here? Then it's going to go to the right because it repels. So these line that you see in here, these electric field line, is basically a direction, like a prediction of what happened if you have another charge nearby. So what if you have a positive charge over here? It will go to this way. What if you have a positive charge over there? It will go this way. So the direction of your electric field line are the directions that a positive tiny test charge would go if you place that positive tiny charge near the main charge that you draw. Now, of course, these lines are actually 3D, and there are many, many more of them. You can draw like unlimited amount of them. Now, this is in, see, is there a way that I can make it bigger? There you go. Now, this is in 3D. So in the middle is your little proton. Okay, so in the middle is your little proton in there. All right. So the electric field lines are the arrows that you see that are going out. Now the reason why the way we draw it, earlier in the book was like this is because we're only looking at like one slice of it. So imagine that if I only show you one slice of that electric field, then it will look like the one that we just draw, right? So it's just arrow going away from the charge. But in reality, it's actually a 3D object, of course. So the electric fields are, if I select low slicing, it's actually like this in space. Okay, very interesting, right? So now each of those arrows just tell you which way you will go if you are a positive charge next to this positive charge. Of course, if you can do this with positive charge, then there must be a way to do this with electron. So in electron, the electric field goes exactly the same way, except it points toward the charge. Which also makes sense, because if the electric fields are a direction that a positive charge would go, then if you put an electron in the middle, then no matter where you put a positive charge, the positive charge would like to be attracted by the electron. So again, if I show you just one slice of it, right, one slice of it, it will look something like this. So this is for a electron. Okay, so for proton, all the arrow goes out. For electron, all the arrow goes in. Does that make sense? Okay, so for proton or for electron. Now, so in our picture, so proton looks like that. Then the electric field for electron looks exactly like this, except that the electric field should be going into the electron, because that is the direction that a positive charge would go. So if you have a positive charge, they will go over there. So these are electric field diagrams. Okay, so protons and electrons have different pictures. All right. Okay, so there is one restriction though. Okay, so there is one restriction, which is electric field can never cross each other. So if I show you two objects, right, together, or if I just show you one object, and let's say I show you one object, let's say like a proton, and then I have this electric field like this, which is possible, but if like one of them goes like this, then you can immediately say that, Mr. Chang, this is the wrong diagram. So for example, you might have a electric field diagram that looks like this. So maybe like that. Now, the moment that you see a point crossing on the electric field diagram, that is wrong. Okay? You will know that, Mr. Chang, this is the wrong diagram. So I ask you which one is wrong. The one that's crossing is wrong. Electric field can never cross each other. Now, why can't it cross each other? Because you have to remember what electric field is, if in terms of like that little test charge, right? That means the little test charge. Now, the little test charge has one goal: follow electric field. That's its goal. Okay, so wherever electric field points, it goes. Now, so imagine this. So imagine this little point test charge goes over there next to the proton, right? And now, so let's say imagine that it goes like next to the proton in here, right? So it will get repelled by the proton, and then we'll follow this path, and then now arrive at this junction point, and then what? But remember, a little positive test charge are supposed to go along with the electric field. But what if your electric fields are actually diverging? So now which one do you follow? Do you follow this one, or do you follow like this one? So that means you have to make a decision on which electric field to follow. But you are just a little protons or electron. You are not allowed to make decision on your own. You are not a conscious being. So therefore, this diagram gives us something that we cannot predict, and that is not what our theory is supposed to be. We should be able to predict which way that little proton will go, that little positive test charge will go. So this kind of diagram is wrong. Or if you ever see an electron with the arrow going outward, then you know it's wrong. Or if you ever see a proton with arrow going inward, then you know that diagram is wrong. Okay, so let's do electric field drawing for, well, actually, let's do a calculation first, and then electric field drawing for multiple charges. Okay, so let's do one question first. So what is the electric field strength? So how strong is the electric field at a point from a negative charge that experience electrical force of 5.3 times 10 to the negative 4. So this one is pretty easy. So if you remember the definition of electric field, it's either electric force over charge or that equation is. Now in here I have electric force. So why not? Right, so I have electric force up here. So why not just use the electric force to find electric field? Okay, so number one, the force is 5.3 times 10 to the negative 4. The unit is Newton, so I see nothing wrong with this value. Okay, so let's this is a negative charge, but you have to learn you don't care about the negative sign. So you have to make sure that you're putting positive numbers in. 2.00. Wait a second, what on earth is that unit? So it's microcoulomb. What is micro? Micro is times 10 to the negative 6. Microcoulomb is not a unit. Coulomb is a unit. So micro just means, divide by a million. That is micro. Okay? So now that equation is correct. So a lot of time you see people getting tricked just a little bit if the unit changes. 265 Newton per Coulomb is the unit for electric field. So just divide. Pretty easy, right? Okay, so a little bit harder then, when you actually have to use the long equation. Okay, so next, a distance, that is just a very weird way of writing distance. There we go. 0.75 meters from a small charge, the electric field is 2 times 10 to the 4. At what distance from this same charge would the electric field be 4.2 times 10 to the 4? Okay, so there is actually multiple ways that you can do this. Now, the easiest way to look at it is this is the unknown charge. I have no idea what on earth that charge is, but it's a charge. It has a charge Q, but I don't know what it is. Now, at a certain distance away, like maybe here, let's draw it closer because my next one is going to be further. There you go. At a certain distance away, R, okay, I know that my electric field at this moment, at this location, is 2 times 10 to the negative 4, 10 to the 4. That's just 20,000, okay? 21, sorry. So 2.1 times 10 to the 4, which is 21,000. Okay, 21,000 is my electric field. All right. Now, they are asking us, at what location will the electric field be bigger? 4.2. Okay, we all know how the equation actually look like. So if you look at the equation for electric field, it's KQ over R squared. Now, in this type of relationship, we can say that the electric field is proportional to 1 over R squared. Now, what does that mean? If R get bigger, electric field actually gets smaller. The fact that we have the opposite. Look, our electric field got bigger. That means R got smaller. That means we got closer. So we got closer in our second location. But how much closer? Well, we kind of need to calculate that. So I know we got closer for sure. You have to get closer to get a stronger force, right? So at this location, our electric field is 4.2 times 10 to the 4 instead of like 2.1. So it's stronger because we got closer to the source of the electric field. Now, how will you actually find out? Okay, so how will you actually find out the new radius? Let's put it that way. Right? This is the new radius. Okay, so the old radius, I don't know how much. The charge, I don't know how much. The new radius, I also don't know how much. That's what we're looking for. Okay, so that is what we are looking for. Now, so what we can do in here is actually quite fun. So what we can do is the following. We know that this equation equals to KQ over R. Okay, KQ over R squared, right? The O1, the O1. We actually are given the O1, by the way. So the O1 is 0.75 meter. That's the O1. All right. Now, the new one. We know that the new one is the same K, same charge, but over the new R. So instead of like the OR is the new R square. Okay. So we know that the new one is going to be like this. Well, that's easy then. So let me show you something. You can take these two equations. Like right here, take this. And then take this. Have you seen someone divide an equation like this? Have you seen dividing equation that already have like both sides on it? It's actually kind of cool. So like look at it. So divide this side by this side and then divide this side by this side at the same time. Okay, trust me, it's cool. On the left hand side, do you realize it's actually just a half? Because 2.1 and 4.2 is exactly double, right? So on the left hand side is just a half. 2.1 divided by 4.2 is a half, right? The bottom is 2, the top is 1. You can tell. Now, what about that nonsense like KQ over R squared, KQ over new R squared? Like, what about this thing? Well, this thing you don't have to worry about. Because didn't you learn, from earlier math that when you divide two fractions together, right? So what happens? You just flip to the second fraction, which is the one in the bottom, and then you end up multiplying, right? So if you look at the same thing in here, so that means you flip the KQ over R new over, and then you end up multiplying, and then what happened is this will be gone. It will be gone. And not only that it's gone, you actually get the R new to go to the top and the R to go to the bottom. Like it will actually look like this at the end. So now you're done. You are technically done. So what do we want? So we have an equation like this. So the equation is 1 is equal to, okay, so we have this equation. 1/2 is equal to R new. Okay, so the new R, which is what you actually have, square, I mean there is a square on it, over the OR. OR is 0.75 of a meter. That's something you already have. Now solve for the new R. Done. Almost don't have to use a calculator, like except for this very last part, right? So you think that at the beginning this is difficult, but then at the end, so you have to take a square root, multiply by 0.75, and then take a square root. So the new distance is 61 cm, which is 0.61 meter from the charge, which if you compare to before, 0.75 makes sense, is slightly smaller. Right? We got closer. Remember, we got closer was the prediction. And now our math actually showed that we got closer. So in this calculation, I think the only surprising thing is how I deal with, this part in here. Most people would think, oh yeah, maybe I need to actually find out what Q is from this equation. You can do that too. Because you have R, so you can do R squared, multiply, divide by K, you can find Q. And then you would say, oh yeah, then I will just use the same Q in here, and I will solve out the R. Sure, you can do that. But if you know a bit of like this, algebraic trick, then you can get to your answer a lot faster and using, your calculator only one time. It's pretty cool, right? If you know that some things are the same, you can actually destroy them like over here, which is pretty cool, right? Okay, now that's for one charge, and now two or more. Okay, what if you have two charges together? Okay, so what if you have two charges together? Let's see if we can use our simulation to look at it. Right, so let's see if we can use our simulation to look at it for now. So if you go to our simulation, if I go to there, and then I select point charge double, that means 2 instead of 1. Now you can see, let's look at 2 proton first. Okay, so 2 proton. All right, so 2 proton in space. Now, this is difficult to look at. Again, let's look at one slice. Not that kind of slice. I want one that cuts through them. Aha, this slice, good. Okay, you see? All right, so every electric field is still going away, right? It's still going away from the positive charge. But then I can even like show you more. There you go. So every electric field is still going away from the charge, but in the middle, it looks like they're pushing away from each other though. So this is the fun part is in the middle, it looks like they are. So if I show you very close to the middle, let's see. Okay, can you see like these? These are all just going away. So there's something weird in the middle, but these are going away, those are going away. Now, let me show you how to actually draw it on this diagram. So technically, they are, well, depending on if the two charges are exactly the same or not. So let's say they are exactly the same. Each of them is 2 coulomb, and they are exactly the same. Then, the line that, they can't really, like, so it looks like there's a line in the middle that they are not touching. It's going to be right in the middle if those two charges are exactly the same. So on this side, you have like going away, electric field, going away, electric field. On this side, then you start to have some of these like, curve like that. So it's almost like they don't like each other. Usually when I draw this, so it almost looks like, oh, don't touch over there, and don't get too close. We are both positive charge. We don't want to actually get together. There, right? So it looks like there's some kind of a resistance, like this. Okay, so now again, you could bring in you could bring in some positive test charge, right? So you could bring in some positive test charge, and then you can ask yourself, which way would that point? Okay, just 1 second. Okay, so now remember, these are the lines that you use to predict what happened to a little positive charge if you bring it nearby. So let's say you have this test charge again, little positive test charge, and you bring it to here. What it's going to do? It's going to be repelled by this and go like that. If you put a positive charge in the middle, it's kind of going to get stuck in here though, right? It's being pushed simultaneously by two charges, so it will stay in the middle. If you put a positive charge in here, what will it do? It will get repelled and go like, phew. So these lines are the direction that a little positive test charge will go. Okay, so notice that electric field lines points always points in opposition to each other. So in opposition to each other. So let me show you what, because this electric field is a force vector, is a vector, right? So when multiple fields overlap, we simply add them up as a vector. So if you do have to add up electric field, you have to do vector adding. So add them up as a vector. Okay, so how about for electrons? So for electron, it looks like this, right? So for electron, you have the electric field going into the charge. So the lines are all the same. Look. So it will look almost the same, like that. But make sure every single arrow points into the electrons or the negative charge, not away. On multiple choice questions, for example, you need to just pay attention to the arrows and see if you can catch one of them that's wrong, then you know that diagram is wrong. Okay, so this is the negative charge version. Now, what if they are not exactly the same size? Which is always, what if they're not the same size? What if one of them is a lot stronger than the other one? So that could happen, right? So a lot of people naturally would wonder, so what happens if, let's say you have two positive, but what if one of them is a lot weaker than the other one? So what if one of them is 2 coulomb and the other one is like 6 coulomb? Like how will you draw something that is unevenly strong in this case? Well, then in this case, the equilibrium line is going to be pushed very close to the weaker one. So it will look something like this. Like a few lines coming out from here. Like that. And then many lines coming out from this one. So how strong the electric field is usually represented by how many electric, or how, close the electric field lines are. So for a charge that is a lot strong, for something that's 6 coulomb, technically it should have 4 times the electric field line compared to something that's like 2 coulomb. Or 3 times, 3 times. Right, but most of the time we won't care about, how many. Just make sure that it is noticeably more. Right? So it almost looked like, just someone very big, picking on a charge that's really small, so it's kind of pushing it away, pushing it to the side. So if you do have uneven charge, then just more electric field on the strong one, smaller amount of electric field on the weak one, and make it so that it looks like, one is being pushed aside. So they don't line up exactly in the middle. Okay. So what if the two charges are opposite? That means what if they attract? Right? What if the electric field attracts each other? So what happens when you have the charges being opposite? So now point charge, so we call it dipole. There we go. So this, see if I can spin it. So this is when, let me show you a slice of it. Okay, I think that's good. Let me just move that a little bit so that it goes over here. There we go. Aha, can you see it? Now from this picture, can you tell which one is actually the positive one and which one is the negative one? Can you tell which one is positive, which one is negative? The one on the which side? Yeah, the one on the left-hand side is the positive one, right? Because if you can see, how can you tell is all the electric field around this is going away from it, and all the electric field around that one on the right is going into it. So you know that this must be the negative charge and that must be the positive charge. And also the arrows make sense. Imagine that my little mouse point is the test charge, right? Of course it's going to go this way because it's going to be repelled by this positive charge and simultaneously get attracted by this negative charge, right? So what if my little mouse point test charge is here? Then it's going to go like and then go into the negative one. What if I start it over here? Then it'll go away and maybe eventually turns around and then get attracted by the negative one. So again, this line shows you what happened if you have a positive test charge. Now I can actually show you the motion, I think, for particles. So instead of, let's not, yeah, so it's going to be like this. So imagine that every single one of those little white dots you have on the screen is a positive charge, right? So they are going to be repelled by the positive charge and get attracted to the other one. Okay, so this is negative, right? So every charge want to go to the negative. They want to go away from the positive because you imagine that these white dots are the positive charge, right? They are the little positive test charge, right? So they go away from it and get attracted by it. Okay, so let me pause it first. And so in here, how do we draw two opposite charge? So it has to go away from one toward the other. All right, so let me pick a color. Let's take purple. So it will be like this. Like the two charges are collected together with electric field. Okay, like this, like that. Go in. So I'll draw a couple first before filling it in later on. There you go. Okay, what did I do wrong? I did something wrong on purpose. I did something wrong on purpose. Can you spot it? The arrows. So one of them is here. The other one is here. Right? That's all right. So you can see every single, like you have to be able to tell, what goes wrong just by looking at the picture and you go like, okay, so look at all the arrows that goes away from the positive charge. Are all the fields going away? So if you see, oh yeah, they're all going away, that's fine. So and then you check the negative charge, is all arrow going toward it? Okay, so should be able to tell, hey, one is not actually doing it. Right, so now we fixing it. So with opposite charge, the two field lines interact, only this time they collect to each other. So the field lines looks like they're collecting to each other, which is that picture. Okay, so we're going to do two easy and one slightly hard question with the equation, and then that's it. All right, so two easy and one slightly hard. So the first two easy, the last one in here with two charges is slightly hard. So let's do the easy one first really quickly, only a few minutes. So we have two charges. Not going to be super easy to begin with. Midway between the two charges, what is the strength of the electric field? Midway between two charges. So we have charge A and then we have charge B. Now charge A is positive, charge B is negative. Okay, so make sure when you draw the electric field, you know which one is which. 2 microcoulomb, 4 microcoulomb, so we have all those numbers in here. So charge A is 2 microcoulomb and charge B is negative 4 microcoulomb. Okay, so negative 4 microcoulomb. There we go. Now, okay, so they say midway, and these two are 0.6 meters apart. So midway means 0.3, 0.3. So I actually don't care about the 0.6 anymore. It would just be 0.3 and 0.3, right, like this. Okay, so step 1, boys and girls, ignore charge 2. Ignore it. Don't look at it. It doesn't exist. Okay, ignore it completely. Now, look at the picture for charge A. You know that it emits electric field like this, right? Around. So by the time it gets to this point, it goes to the right-hand side. So this is the electric field at that point from charge A, right? It goes through that point to the right-hand side. Okay, so now I don't need any of these distractions. I just need the one that is actually over there. So from charge A, at that point, the electric field is going to the right. Why is it going to the right? Because this is the positive charge, and positive charge always have electric field that goes this way, this way, this way. So the one that goes through that point is going to the right. All right, now we can find that answer with just one equation. So that should be easy. So how do you get EA, electric field from charge A? That's easy. That's going to be K charge A over R squared. What is charge A? 2 microcoulomb. What is K? 9 times 10 to the 9. So these are all numbers that we can get quite easily. 9 times 10 to the 9, and charge A is 2 microcoulomb. Make sure micro is -6. There we go. Divided by distance, 0.3. Make sure you have a square. So that's something your calculator can do. About 200,000 is the answer. Roughly 200,000. Okay, so there we go. And it goes to the right-hand side. So right-hand side. There. Now, part 1 done. Part 2. Ignore charge A. Now, so imagine that charge A doesn't exist, and it's just all an illusion, right? So charge A doesn't exist. Okay, so now only look at charge B. Only look at charge B. Okay, so from charge B, which is a negative charge, I have, what does the electric field on negative charge look like? It goes into the negative charge, right? So it goes into the negative charge. So at the point that it goes through that corner, so at the point that it goes through the middle point between the two charges, that electric field from charge B happens to be also pointing to the right-hand side. Okay, so also points to the right-hand side. So you have another one that also points to the right-hand side. Now, you can almost think about it like as something like this, right? Imagine you have a positive charge in here. Doesn't it get pushed to the right by the positive charge, but at the same time attract to the right by the negative charge? So imagine if there's a positive charge in here. Doesn't it get pushed like double time that way? Because A would like to repel it, B would like to attract it. So together, is still going to the right. So this is your electric field B coming from charge B. And that also points to the right though. So that means once you get the answer, they should be added. The picture tells you add or subtract. Don't rely on the equation for anything. The equation gives you the number. So for example, in this case, 9 times 10 to the 9 is the Coulomb constant. The charge is 4 microcoulomb. Mr. Chong, you forgot negative. No, I did not forget negative. I don't care about the negative. Only magnitude. Only magnitude. The picture tells me I should add them, and I don't need the equation to tell me no. Okay, I am adding them. So 400,000 approximately Newton per Coulomb. The picture tells me that also goes to the right. So therefore, add them. If one goes right, one goes left, subtract. Both go right, add. So the total electric field is EA plus EB. And because they both go to the right, you literally add them. 600,000. Newton per Coulomb, right-hand side. Okay, so you don't use the equations positive and negative sign at all. Okay, so in 2D, it's a little annoying. I agree. So next, you have two charges that are exactly this, or not exactly the same, but they're both positive in the next example. Now again, so the game is the same. Draw the two charge, find out where the point is, draw the electric field on that point, see if you need to add or subtract, find the electric field, and then do the adding or subtracting. So two charge that are exactly the same, 5.2 microcoulomb is here. Now they are exactly the same charge though, so A and B are the same. 5.25 microcoulomb, both of them. Okay, 5.25 microcoulomb, both of them. 0.4 meters apart. Okay. All right, we have to figure out distance. So I will erase these later on, but for now, let me put it in. 0.4 meter here. What is the strength of the electric field at the point? That is 0.1 meters away from the first charge. So here, 0.1 meters, like here. So this point. So this is 0.1 meters away from the first, 0.3 from the second. There. Okay, so you don't need to know like the location between the two charges. You need to know the location between the point that you want and those two charges. So you always use the location of the two charges to just figure that out. Now, so this is like your radius or your distance B and distance A, right? So the reason why we separated. Okay, let's look at the electric field. All right, which way does EA point and which way does EB point? On this point. Which way does EA point? Right. Yay. Yep, it goes to the right. EA goes this way. Now, why does it go that way? Because this is A. Its electric field goes away from it. So at the point that it goes through this location, it happens to be going to the right-hand side. Right? The electric field on the positive charge always looks like that. So when you go through that point, it happens to be going to the right-hand side. So now if I erase everything else, except for that one, you should see. Okay, what about EB? EB is also positive. So its electric field also go away like this. So by the time it goes through that point, it goes this way. Oh, it goes left. Yep, that one goes left. Oh, that means we have to subtract, don't we? Yep. Instead of adding, subtracting. So this is EB. So our EA and EB this time is in opposite direction. Question number 1 for you. Why, even though those two charges are exactly the same, I on purpose draw EA a lot larger than EB? How far are you? If you're close to one, you get more effect by that one. If you're far away from B, then you get less affected by B. Any forces are like that. We are close to the Earth, so we are attracted by the Earth a lot more than we are attracted by the Moon. Right? I mean, if we are on the Moon, we'll be more attracted to the Moon by the Earth. So this point that they pick is a lot closer to the first one, so the first one's A's effect should be a lot greater. So this is from the A, and that's from the B, right? So B should be, I mean, you're so far apart, so it should be weaker. So now, just use some magical algebra to figure out EA and EB, and then subtract them. Even though they both turn out to be a positive number, you don't care. You subtract them. So 5.25, why are you subtracting? Because they point in opposite direction, even though they're both positive. So K, Q over R, which is 0.1 squared. That's 1. Right, so K, Q, so times 10 to the negative 6. So KQ over R, this is now 0.3, and then we square. So one of them is 0.1 squared, one of them is 0.3 squared. There we go. And now get both of them. And which one goes left, which one goes right, you just need to write it down. So this is 4725000, that's 4.7 million. 725000 Newton per coulomb. This is the A, which goes to the right. And then the next one is 525 0 0 0. You see, this one is a lot weaker. It's 9 times weaker. This one goes to the left. Okay, so this is the blue one that goes to the left. So the electric field going to the right is 4.7 million. The electric field going to the left is only 500,000. And the winner minus loser, I guess, right? Just like our net force. So the total electric field is going to be the winning one minus the losing one. And take the direction of the winning one. So it's about 4.2 million. Okay, 4.2 million Newton per Coulomb. And the right hand side prevail at the end. Okay, so those two are the easy one. Okay, so those two are the easy one. So which one is slightly harder? The next one is slightly harder. How much? Not much. It's actually a lot like what you just did on momentum as a chapter. Now, except you're not adding momentum, you're adding electric field that are pointing in 90 degrees from each other instead of like away, directly away from each other, or you can add them. So what happens if they are sitting like this? Okay, so now it's 3D. Now let me rewrite the numbers because I think my picture looks weird. This is 12 micro. This is negative 8 microcoulomb. So I think your pictures are fine. Like my pictures go up. And the point P is over there. My drawings are very screwed up. Point P is over here. Okay, so this is A. Let's name them. I have a hard time remembering which one's which. A and B. Okay, now A is positive. So at point P, the electric field should be going down. I mean, down or south, I guess. Down. Let's say go down. It must be going down, right? Because this is a positive charge, so the electric field just keep going like this. So by the time it goes to P, it must be going down. So going down. So we just have to make one calculation. The one goes down. Okay. And let's call it EA. Electric field from A. Now B is a negative charge, so the electric field goes into it. So at point P, it's going to go into B like that. So this is EB. Okay, so once you get EA and EB, which is just two calculations like what we did earlier, you can vector at them. Then you're done. Vector at them. Okay, so EA is K, charge 1, which is 12 microcoulomb, so 12 times 10 to the negative 6, divided by distance, 6 square. There, right? So PD easy. Turns out to be about 3,000. Convenient. Direction is down. Okay, so direction is going, you know what? South. Let's say south. Right? I mean, down is such a bad way to say it. Then the next one, B. Same idea. K. The charge is 8 microcoulomb, but again, don't put the negative in there. The direction doesn't make any sense, and you don't need the negative to confuse you. 4.5 square. So that turns out to be 3,556. So the other one is 3,000. This one is slightly greater. That one goes to the east. Right, so we have one south, one east. Now the remaining part of the calculation is something that you should know how to do. You have an arrow that goes south with a magnitude of 3,000. You have an arrow that goes east with a magnitude of 3,556. So your overall total electric field must be this arrow right here. So Pythagoras theorem. And then give me this angle. So this is your total electric field. And then your angle. Right? So all of those can be obtained just by using Pythagoras theorem. So a squared b squared equal to c squared, right? So you get E total square equals 3000 square plus 3556 square. You can take a square root. So your total electric field is 4652 Newton per Coulomb. You can also get the angle, which is from tangent. So inverse tangent, opposite 5, 6. Opposite is actually the red one, 3, 5, 5, 6, over adjacent, which is 3000. And that gives you 50 degree. East of south is touching south. Yep, east of south. So your total electric field and direction. There you go. So imagine that if you actually have a electron at point P, but hold on. Imagine if there's actually a proton, which way would the proton go? So as you can see, the proton will be going this way from the same electric field. So you need to get force, which is easy. Remember, electric field is electric force divided by charge. So if you want the force, it'll be like this. Okay, so you can get your force like this just by multiplying the electric field by the charge of a single proton, because they say we are putting a proton in there. So multiply the electric field of the charge to the charge of a single proton, we can get the total force. So the total force happens to be about 7.4 times 10 to the negative 16 Newton. So very small amount of force. But remember, the electron is extremely light though. So even though the force is small, if you do acceleration, which is ma, right? So force equal to ma. So if you want acceleration, you would then take the force and then divide by the mass of a proton. Mass of the proton is tiny. 1.67 times 10 to the negative 27 kilogram. So once you divide it, you get an acceleration value that is surprisingly large. About 4.5 times 10 to the 11 meter per second squared. Now remember, regular force of gravity acceleration is 9.8. This thing is 450 billion meter per second squared. In the same direction of the force, of course, right? But don't worry, it still won't go over the speed of light. Just, whatever we learned in last chapter. Fast acceleration doesn't mean you can go faster than the speed of light. That means you get to very close to the speed of light fast. But then you get stuck there because you become supermassive and you can't accelerate anymore. Okay, so let's stop there.